So I want to get a better sense for the background for this crowd. So clearly you're in the machine learning 2.0 track, so I presume you're interested in machine learning. But how many folks have known about deep learning or are using deep learning in practice, but just by show of hands? All right, cool. And I guess how many folks know about convolutional neural networks by show of hands? All right, great, got it. All right, so I guess it was advised to me by John Langford that I start slow and walk you through some of the basics of deep learning and convolutional neural nets. So we'll start there. So I'm going to just briefly talk about the history of deep learning, why it's important, commercial applications at this point in time, and then convolutional neural nets. And then we'll get to the meat of the talk, which is about climate science, why we care about this problem, and then how we represent climate patterns using supervised and semi-supervised architectures. And then I'll get to scaling deep learning on our supercomputer. All right, so let's start with deep learning. So for those of you who are tracking the field, you may know that this is not the first time that neural nets have been, have been popular. So they started off in 1960s, and at that point in time, people were essentially fiddling with mapping input layer to an output layer by using one hidden layer. So essentially, what researchers used to do was to take the input, multiply it by a linear weight, and then apply some nonlinearity, and hope that you'll get an output. So they experimented with this for a while, and essentially, unfortunately, early on it was discovered that such networks could not even solve something called the XOR problem, an exclusive OR problem. And unfortunately, that result was widely publicized, and a lot of people were disappointed that these neural nets would not do anything complicated. In the mid-1980s, a bunch of researchers kept at it, so they started looking at multi-layer networks, so not just having one hidden layer, but a cascade of several hidden layers. The idea still being the same. So you take an input, you apply a linear weight, you apply a nonlinearity, and then the output of that first hidden layer would get processed by the second hidden layer, and so on. They also worked out how to do backpropagation. So how do you take, if you're making any mistakes at the output layer, how do you move the error, or the correction rather, to the weights through the network and update the weights to get a more accurate answer. So that seemed to hold some promise. Now, unfortunately for the neural net crowd, support vector machines and random forests were in vogue, and that's what dominated the field for the next 2 decades or so. Till present day. So we are right now in the midst of, I guess, the third wave of neural networks. And one might ask the question of what's different this time around. There are two important things that have changed between the mid-1980s to present day. One is that we definitely have big data, and we have a lot of it. It's complex, but perhaps more importantly, there are a lot of labeled data sets that are now available. So the computer vision community, which for the first time demonstrated that deep learning is extremely powerful, had access to millions of labeled images. And once you have that, then it's been found that these systems can be really powerful. The other change is big compute. So certainly, Moore's law has been alive and around for several decades now. So certainly on your laptop, you can have a powerful GPU, or you can have a many-core CPU and get access to teraflop class computing. So with these two trends, a lot of labeled data and a lot of compute horsepower, essentially people started exploring, what if we start adding more and more layers to the network? So here is an input, and right at the end is the output, but you'll note that we no longer have 2 layers, but we in fact have dozens of layers. And essentially, I think what the field empirically found was that if you can do that, if you can have a very deep network, then these networks are extremely powerful in terms of capturing patterns in your data set. And they've applied it now successfully to a range of applications. So I'm going to just walk you through some commercial, some bleeding edge research. So the DeepMind startup was acquired by Google, and immediately they put it to use to defeat the human world expert in the game of Go. So Go is a game that's supposed to be exponentially harder than chess, and using a formalism called reinforcement learning, we now have beaten the Korean grandmaster and now the Chinese grandmaster. Self-driving cars are no longer fiction. In California, at least, these cars are routinely on the highways. So certainly there are a range of sensors that the cars have. So there might be computer vision sensors or depth sensors. Processing all of that data and fusing it is done by deep learning to some extent, but also the control strategy for the car. Should I turn my wheel to the left or to the right? Should I press the accelerator or the brake? That's determined by a deep learning system as well. Deep learning has certainly become quite transparent. So these days, if you just pick up your cell phone and you talk to it, chances are high that there is a deep learning system either on your cell phone or somewhere in the cloud. And it's going to be essentially trying to understand the speech signal and figuring out what question you have in mind. So this is fully transparent at this point in time. But really, the key event that revolutionized, I would say, deep learning and made it successful was computer vision. So in the computer vision community, there's something called the ImageNet competition. And the competition is as follows. We're going to give you a bunch of images. So these are all natural, real-world images. And you, the computer system, will need to come up with, well, you need to tell me exactly what objects are there in that image. So given this image on the top left, the deep learning system needs to draw a box around a bird and a box around a frog, and so on and so forth. Now, before 2011, the entire computer vision community had been at it for several decades. And every year, the error rate in this particular competition would drop by maybe 0.5% or 1% or so. So it was really a slow, incremental field. Till Jeff Hinton and his colleagues in Toronto applied convolutional architectures to dramatically drop the error rate in 2012 by using deep learning by about 15%. And subsequently, the entire field has almost entirely shifted over to deep learning. And they have beaten up on this problem to the extent now that the error rate that's reported by these convolutional architectures is below that of human performance. So essentially, a machine can do a better job in identifying objects and images than even humans. So I want to just walk you through, I guess, some of the basics of how this works in practice. So typically, what happens is that you start off with an image that's all the way off to the left here, and that might be, say, a 224 by 224 pixel image, and there might be, say, 3 channels. Typically, when you're looking at commercial applications, you have RGB channels, and it's 8-bit. And what you want the network to do at the end is to produce its estimate of what it thinks there is in the object. So perhaps there is a vector with 100 classes, and it's going to give you a probabilistic estimate of what class it feels most confident about. So the way you set this up is, the very first thing you do is to identify training data. And the more of it you have, the better the chance that you're going to converge to something interesting. So training data means that you'll need a lot of images, preferably hundreds of thousands, if not millions. And you'll need labels on what exactly is in the image to begin with. Somehow, you'll need to decide on what architecture makes sense for this problem. And that's where some of the magic certainly is. But let's say that you have some heuristics or some other people in the field have already fiddled with similar data, and you have a reasonable starting point. So you essentially determine what architecture makes sense for this problem. Now, once the architecture is set, what you'll do is, and typically the architecture consists of different layers where filtering and pooling happens. So I'm just going to visually, these are standard image processing terms. But essentially what you do is, say you have an input image with 3 channels. You're going to define some filters. They might be, say, 5 by 5. And you're going to slide those filters across the image till it produces some feature map output. So that's standard convolution. And then there are some non-linearities, such as pooling. So you take an image of here. And then in this case, we're going to apply something called the max pooling operation. So I apply a max pooling operation to these 2 by 2 pixels. The max value is 9, and so on and so forth. So generally speaking, those are the 2 kinds of operations which are applied in these convolutional architectures. So essentially, you design a cascade. So you have convolutions, and then max pooling, convolutions, max pooling, all the way till the end when you have a fully connected layer. Now, the key thing here is that you are not going to be designing these filters by hand. And this is a big difference between what the computer vision community did for 3 decades compared to what the deep learning crowd tells you. The computer vision community thought that it could, by hand, design the world's best pedestrian detector and the world's best tree detector or car detector and so on. What the deep learning folks said, no, we're not going to do that. We are not going to be in the business of designing filters. We're just going to initialize these weights randomly. And then we will take our training image, we will pass it through this entire network, and we will get an output. Now, chances, of course, are high that if you start off with a random weight, you'll get junk. So you will make an error right at the end. But because you know what the truth is, because you know what the label is, you can compute what the error is, and then you can back propagate. You can figure out the gradient of the error with respect to the layer, and then you can back propagate that gradient through the network and adjust the weights so that hopefully it'll do a better job next time around. And then you do this millions of times, as many images as you have. And you hope that you converge on a reasonable architecture. So anyway, so we started with random parameter initialization. We do a forward pass, filtering images and making the prediction. We compute the error because we know the truth. And then we do the backward pass. We compute the gradients and update parameters. Now, what got people really interested, I would say, I think intellectually, was that if you apply this technique, this procedure, to real-world images, you get filters that are really interesting, and they make a lot of sense. So right at the very first convolution layer, essentially what the network learns are low-level Gabor filters. And neuroscientists believe that this is what our visual system does. So these are all oriented edges at different scales. A little bit further, the convolution in the convolutional layer, essentially what the network learns are compositions of these low-level features, so simple texture patterns. Move further along in the architecture, the network seems to pick out object parts. So it'll take these relatively simple texture patterns and then learn how to compose them to make parts. So it'll learn the representation of a clock or the wheel of a car or the face of a dog and so on. And right at the end, the network essentially learns the notion of an object. So perhaps there is a ship or an animal or what have you in the network. Now this was really interesting because this was not prescribed in any way, unlike what the computer vision community had done for 3 decades. There was no notion of a prescription of these are the filters you need to have in order to become, in order to design the world's best car detector. All right, so hopefully I think that gives you a sense for just the basics of these architectures, what's involved. So I'm going to now transition to, from commercial applications to climate science. I'm, as Soups mentioned, so I'm at Berkeley Lab, and we really are not in the business of making money. We care about basic science and fundamental questions. The science question in this case is, we know that the climate is changing. Politically, it may be convenient or not is a different question, but the climate is changing. And instead of talking about maybe a simplistic quantity like the change in temperature by 1 degree or 2 degrees or a change in sea level, the question that we want to ask here is, how is extreme weather going to be changing in the future? So what do we mean by extreme weather? So for this city, at least, I guess some of you might still recall Hurricane Sandy and what happened when Sandy made landfall. So this was a storm system that started off in the tropics, and it started propagating towards the northeast. Now, unfortunately, there was another storm system to the right of this figure, which prevented this storm from typically veering off to the top right, which is what it would have done normally. But instead, it made landfall with catastrophic effects. So certainly, people on the coastline, individual homeowners, so on and so forth, were negatively impacted. Certainly also impacted a number of landmarks, I guess, in the area. But a city like Manhattan was at a standstill for several days. Now, a city like New York, again, is very resilient. The economy is really strong, so it can always bounce back. But hurricanes do not discriminate. I guess almost a decade back now, Hurricane Katrina made landfall in New Orleans, which is perhaps economically not as strong a city. And it almost, I would say, it took a decade for the city to recover. Now, both of these events, Sandy and Katrina, are order $10 billion events. I mean, that's the amount of damage they cause. But really, it's not just about the cost, the dollar amount of the damage. It's really the inconvenience that it causes to humans. I mean, fortunately, lives were lost, and a number of people displaced from their homes. So I think this is the Houston Astrodome, and a number of people were moved there in the aftermath of Hurricane Katrina. So the question here is, we know that these events are extremely expensive and extremely, there's a negative impact on humanity. What can we say about such events in the future as the climate change? So we're not going to be talking about a coarse quantity like a degree or 2 Celsius increase or sea level rise. I mean, those are important things to keep in mind. But the question we're going to ask is, are Category 4 and Category 5 storms going to be more frequent in the future? Are they going to start making landfall more often in the future? When they make landfall, are they going to be more intense or less intense? So those are the questions we're going to ask. So how do we go about answering that question? Well, as we often do in earth sciences, our lives are relatively short. I mean, the recorded time period for humanity is relatively small. Earth is several billion years old. So one of the things that we can do is to look back in time and look at paleoclimate records and see if such events have happened. Now, those are hard to come by, and you can only dig for these kinds of records in very few places in the world. But now, because we have powerful computers, one of the things that we can do is to simulate the Earth going forward. So we can have climate simulations, and we can plug in a range of effects. So we can talk about what the external forcings are for the climate system, so solar activity and volcanic eruptions. We can talk about anthropogenic influence, so how, say, the GDP of China and US and India are going to grow, how much CO2 emissions they're going to make. And then we have a lot of physics equations that we plug in, and those take into account the internal climate system variability. So you plug all of that in, and then you run the climate simulation out for the next 100 years. So essentially what you're going to do is, once you do that, you end up with a large data set. And we will need to do some pattern detection on that data set. So I wanted to give you a flavor. I understand that most of you may not have a background in climate science. So I wanted to give you a flavor for what the data set looks like. And the question you should be asking yourself as you see this movie is, if I have 100 years of this movie running in front of me, will I be able to find patterns in this data set by hand or by eye? So there is a certain field called water vapor humidity or specific humidity that we're trying to visualize. This is a model that's our production workhouse model in the DOE, and we run this at 25 kilometer resolution. And essentially, you're seeing the atmosphere. You're seeing how water vapor in the atmosphere is getting transported. Some of you may note that there are hurricanes that are forming, and they, some of them fizzle out here, but others develop and grow and make landfall. The movie that we played was just over 3 months in a specific year. But now, imagine a movie that runs for 100 years. So you have a lot of data to process. Now, if you look at any specific patch in this frame from the movie, you're not going to have 8-bit RGB information. You will actually have a lot of variables of interest, and these are all going to be single or double precision floating point. So you might have specific humidity, but then you might also have wind and pressure and temperature and so on and so forth. So essentially, this is what the machine learning or the deep learning system is going to see. And based on that information, it'll need to decide whether there is an extreme weather event here or not. So the task is going to be, I will give the deep learning system these fields, and then the deep learning system will need to say, draw me, the task I'm going to ask it to do is to say, draw me yellow bounding boxes around hurricanes, and draw me green boxes around extratropical cyclones, and draw me red boxes around atmospheric rivers. These are all different kinds of examples of extreme weather events of interest. All right, so there is an analogy here in the task that we have in climate, which is to find these patterns. In computer vision, when I showed you the ImageNet challenge, it was roughly the same problem. I had RGB images, and I had to pull out pictures of cats and dogs and so on. So it's a pattern classification task. But there is also this key step of feature learning. The climate community has not spent 3 decades in hand tuning features for different types of events. They have actually spent 3 decades in designing features for one event, but not others. So I really want to automate this. I really want to get pattern classification and feature learning working at scale. Now, so there is an analogy, but then there are some differences. And as I mentioned, there is the attributes of climate data are different. So we have many channels. So we have dozens of channels. They're all double precision floating point. And then probably the last bullet point is most interesting, which is that the underlying statistics of patterns are likely different. So if you think about taking a camera and clicking images in the real world, perhaps your camera has 1,000 by 1,000 pixels. So you take an image, so that's 1 point in a million dimensional space. Now I go around taking a lot of pixels, so I'm slowly filling in points in this high dimensional space. And essentially what the deep learning system does is it tries to figure out how can I separate clusters in this high dimensional space. Now in climate, roughly is the same story. So maybe we have 1,000 by 1,000 pixels. And now I'm going to be looking for patterns in this data set. There is really no guarantee a priori that patterns in this high dimensional space corresponding to a fluid flow system will be the same as what you find in the natural world. So the underlying statistics are most likely different. And the question really is, can a deep learning system be successful at separating out patterns in this space? All right, so that leads us to representational challenges. I mean, given this problem setup, how do you go about solving it? So we're going to use two approaches. First, because this is the first application of deep learning to a climate science data set, I needed to convince myself that convolutional architectures would work at all. So we're going to start slow. We're going to start simple and say, let's try supervised convolutional architectures. And then once that works, then we'll try semi-supervised architectures. So let's start with supervised learning. So again, supervised learning is the paradigm wherein you have a lot of data and you have labels for that data set. So our training input is going to be nicely cropped, nicely centered patches that have labels. So I mentioned that the climate science community has spent a bunch of time, say, trying to better understand tropical cyclones. So we have some heuristics that the community seems to have converged on, which we code up, and that's what we use for producing labels. Similarly, people by hand in some cases have manually annotated and said, oh, I know that there is a certain event that happened on a certain date that hit California and so on. So there are very few examples of these, but they do exist. Now this list is not exhaustive. We actually have dozens of extreme events that we want to track. And one of the goals here is going to be to get at the other classes of events. But we got to start here because we need to be able to operate on a fluid flow simulation output and see if we can find patterns. All right, so for simplicity, how about we just focus on tropical cyclones? So I have nice cropped centered patches of the simulation data set. So I give it labels. So I say this patch contains a tropical cyclone and this patch does not contain a tropical cyclone. So this is a classic binary classification task. That's all that the network needs to do. So once the network has trained itself on, say, 10,000 positive and 10,000 negative examples, I'm going to give it some held out data, some held out test data. And then I'm going to ask this question. Well, how well do you think that this new patch has a tropical cyclone in it? A yes or no? So that's going to be the binary classification task. All right, so some details on the image patch size, the variables, the channels that went into this, and then how many examples we were able to provide. Now, you'll note that we do not have 100,000 or 1 million examples. So that's always going to be a constraint to keep in mind. Perhaps this constraint applies to some of the applications, commercial applications that you care about. Now, what we ended up doing, again, by some experimentation, we figured out, so given that we don't have a lot of data, what sort of a relatively shallow architecture could actually solve this problem. So for tropical cyclones, we figured out that 2 convolution layers interspersed with 2 max pooling layers, and then a fully connected layer right at the end seems to be sufficient for solving the problem, and it does not overtrain or overfit the data that we have. And a similar story holds true for the other 2 patterns that we care about. Now, here are some results. So this table essentially lists accuracy. So for the test data that was held out for the binary classification task, what percentage of the time was the deep learning convolutional architecture able to correctly classify tropical cyclones. So the convolutional results are all the way to the right, and then we, for due diligence, we did implement random forests and support vector machines and k-nearest neighbors and logistic regression. And generally, I would say that indeed, convolutional nets do get the best performance. But I guess the fact that was not appreciated by me till I coded up the other methods was that it turns out that this is a hard problem. Most of the numbers here are above 85% to begin with. So I think this is a really important lesson learned, which is, one should not use the most powerful hammer there is right now, which is deep learning, on any single data set. You could probably start slow, start with something that's interpretable, like logistic regression or SVMs or k-nearest neighbors, get a sense for how hard the problem really is, and then move out to deep learning if you really need that extra accuracy. I'll note that all of these methods have some free parameters that you need to tweak. So for k-nearest neighbors, perhaps there is the choice of k that you need to somehow decide upon. For support vector machines, you need to decide on the form of the kernel function, for example. Random forests, you need to decide on how many trees you want to have and how much, what the depth of the trees should be, and so on and so forth. Convolutional architectures, of course, there are many more parameters you need to decide upon. So there is a tool called Spearmint that we've been using with some success at NERSc. So for all of these methods, we use Spearmint and we figure out what the best choice of parameter might be, and then we go with that choice and then proceed with the training. All right. So anyway, I think so far things are promising. I think I convinced myself that supervised convolutional architectures could work on the output of a climate data set. So let's take it up to another level. So for semi-supervised learning, what I would really like to do is, instead of having 3 different networks that do a great job at finding 3 separate patterns, I would like to have one unified architecture, a single network that can find all weather patterns. I would like that network to not just do binary classification, but I would like it to predict where the bounding box is. So I need to find out where the center of the pattern is and then the spatial extent of the storm. And then this last point, this is sort of the holy grail, which is I know going in that I'm going to be able to provide only labels for, say, 3 kinds of events. But I know that there are many other types of events for which I don't have labels. So I would like to build into this architecture the capability for it to discover new patterns. So this is the convolutional architecture that we ended up with. So on the left here is the encoder. So this is the classic picture, the ImageNet picture, or the supervised picture that I showed you earlier, a bunch of convolutional and pooling layers and so on and so forth, till you reach a certain compact representation of the weights. Now, we'll just stop here for a moment, ignore the piece on the right. But just if you look at the green piece on the bottom, we're going to be operating on this compact representation, which is called the bottleneck layer. And we will ask the bottleneck layer to predict bounding boxes, so that's a regression task, and then also predict labels, that's a classification task. So that's what we're going to do. So from left to the bottleneck layer to the bottom, the green box, this is a classic supervised problem. Nothing new there. The piece that's new is the part on the right, the decoder piece. So essentially what the decoder piece does is it operates on this bottleneck layer, and then it's going to progressively, in some sense, I guess, upsample the features which are learned here till it gets an image which is of the same dimensions as the input image. And the objective that it has, the objective of the decoder piece, is to make sure that it can minimize the reconstruction error between the input and the output. So this network is essentially trying to do 2 things at the same time. One, from left to right, so this is called an autoencoder. It will take the input, filter it down, filter it up, and try to minimize the reconstruction quality between the input and the output. And the second thing it's going to simultaneously try to do is to, for the given patterns for which it has labels and bounding boxes, it will try to do the supervised classification and supervised regression task. All right, so we coded this up, and in general the results look reasonable. This is pretty much work in progress. On the left are 16 images, which is just a snapshot of a certain time instant in the climate data set. So these are all different fields. And on the right, the panel of 4x4 are the reconstructed variants as the output of the autoencoder on the right. So in general, I would say that the spatial patterns are being captured quite well. Now, how about the classification and regression task? So in this case, ground truth is in green. So all the green boxes here with the TC label means that there is we know that the ground truth is essentially a tropical cyclone at that location of a certain bounding box size. There is a green bounding box here for an ETC. There is a green bounding box here for an atmospheric river. And the network, again, the single network, is now trying to predict these three classes. So in this case, it's predicted an extratropical cyclone here. It seems to line up pretty well. It predicts an atmospheric river here. The bounding box is not quite sized right, but at least the position is fine. And it does maybe a reasonable job in these locations as well. So there's work to do, but it seems to be getting the patterns right. Now, how about pattern discovery? Again, this is sort of the hard one. So I talked about this bottleneck layer, and again, to the extent that this network is doing the right thing, we should be able to cluster the features that the bottleneck layer has learned, look at the clustering structure, and see how well the clusters corresponding to known events are separated. So in this case, blues might be extratropical cyclones, and red might be tropical cyclones, and greens might be atmospheric rivers. And I apologize for the quality of the display here, but the gray dots are different other feature vectors. The colored ones are features that we know correspond to label data. So what I was hoping, and to some extent I think it's true, the blue stuff is interspersed throughout, but definitely the green stuff is slightly separated. And some of these areas, so this chunk here, definitely corresponds to tropical systems that are evolving. And this chunk here corresponds to weaker systems. So I know that this is not perfect, but eventually I think our hope is that if you can get a good separation of clusters in this low dimensional space, then the question then becomes, if we find a tight cluster which is separate from these known labels, can we associate a new semantic label, semantic type to that cluster? So that's our hope for discovering new patterns. All right, so I think hopefully you have a sense for that we made some progress along by using supervised convolutional architectures, also semi-supervised architectures. Now the problem is scaling. How do we get these things to run fast? So again, for those of you who have some experience with deep learning, you may know that it takes a long time for these networks to converge. So in our experience, I think when we apply it to scientific data sets, if you want to process, say, tens of gigabytes of data, it can easily take several days for the networks to train. And we, at this point in time, we easily have tens of terabytes. I mean, the climate data set that I'm showing you is 30 terabytes in size, and there's more waiting to be processed. So if it's going to take you weeks and maybe months to train your network, then you're really not going to be able to experiment at all. So I mentioned this hyperparameter tuning problem, which is you have to come up with the right architecture to begin with. And the hyperparameter choices might comprise of how many layers do we have, how many filters do we use, the size of the filters, something called striding, the kind of nonlinearity you want to apply in the pooling layer, the learning rate that you might want to apply. Sometimes people change the learning rate as the training proceeds, choice of different optimizers, so on and so forth. So this is a 7 to 8 dimensional space that does need to be explored somehow. But if each run is going to take a week or a month, this is just not happening. So anyway, performance, so single node performance and multi-node scaling is absolutely key going forward. So I guess I just want to share the stack that exists, the deep learning stack that's there in practice right now. So as a practitioner, there are a number of frameworks that you can use, and TensorFlow and Caffe and Theano are the ones that we use at the lab. But there are higher level frameworks where it's much easier for you to set up a network easily, like Keras and Lasagna. Now, as you think about scaling, actually much of the magic is underneath the deep learning framework. So there are multi-node libraries that you have to keep in mind. So perhaps you can use MPI or gRPC as a library. Intel has now developed a new library called MLSL. Now, single node performance is absolutely key. So if you're using a GPU, then cuDNN does a really good job at getting you that performance. But on a CPU, you will probably need to turn to MKL. And hardware, of course. So we use Knight's Landing. There are other flavors of multi-core CPUs coming up shortly. And GPUs are, of course, a very competitive option at this point in time. So for all the scaling results that I'm going to talk about next, the stack for us is going to be Caffe, and in particular Intel Caffe. We used MLSL as the multi-node library. We used MKL for single node performance, and then Knight's Landing is the chip that we used. So a few words, I guess, on the target hardware platform. So I work at the NERSc Supercomputing Center, and the machine that we ended up using for these tests was the Cori Cray XC40 supercomputer. And this machine has 9,600 Knight's Landing nodes. So in theory, it's capable of 30 petaflop class performance, hundreds of terabytes of memory. I/O is a challenge for deep learning, so we ended up staging a lot of our data not on a Lustre or a GPFS file system, because those typically don't keep up. But we ended up using a big SSD pool called the Data Warp, which is 1.5 petabytes in size, and it can support I/O rates of 1.5 terabytes a second. So a little more specifics on the input data set that we ended up using for this study. So the input images are 768 by 768 in size. They have 16 channels. Overall, the data set in aggregate is 15 terabytes and is comprised of 400,000 images. And the architecture that we ended up using has 9 convolution layers and 5 deconvolution layers. And the parameters, all of the filters, the weights, are about 300 megabytes in size. All right, so on the single node side of things, I mentioned the Xeon Phi, the Knight's Landing chip. We used Intel Caffe with the MKL 2017 library. We did have to optimize various layers. The deconvolution layer in particular was not yet optimized for KNL, so that's something that we ended up doing. And this is the performance that we get for our architecture. So a couple of, I guess, 2 things are being plotted here. In red is the amount of time that's been taken up by different layers. So there are a bunch of deconvolution layers in the backward pass and convolution layers in the forward pass and so on. So red indicates how much time is being spent in various layers. And in black, the vertical plots are what the performance level is in terms of the teraflop rate that we are able to achieve. So in general, we are able to get anywhere from 1 to 4 teraflop on a single KNL node after we did the optimization, which is not bad. There's only so much room that you have on a KNL chip, and I'll note that some GPUs, of course, can do more on a single node basis, but 1 to 4 teraflops is not bad at all for KNL. So the real piece here is in the multi-node strategy. So now that we know you can get 1 to 4 teraflops on a single node, how far can you really push it out across this 9,600 node supercomputer that we have? Now, a few options. One is to use data parallelism, wherein you take this 400,000 images, and then you're going to just break it up into pieces, and each node is going to be processing a small fraction of the image, a small fraction of the data set. So that's the typical data parallelism strategy that's used, and that's what we're going to be using for this exercise. Now, some researchers also use model parallelism, which is we're going to take a big network. We'll actually break up the network into pieces, and perhaps have the same data set on different nodes, and we'll figure out a way to get the networks to synchronize with each other. All right, so a bunch of optimizations here. I'm going to walk you through some visuals for these optimizations, but it was really important to get to develop a hybrid strategy for synchronizing parameters. We had to do some topology-aware placement in putting the parameter servers, and then we had to dedicate some nodes purely to play the role of a parameter server. I'll note that just like we use Caffe for the single node stuff and MKL 2017, in this case we used the new MLSL library, which gets much better performance compared to baseline MPI in terms of bandwidth utilization on our network. All right, so just some visuals. I guess there are 2 options, 2 extremes perhaps for converging on parameters as different nodes see data sets. So some conventions here. So a worker node will see a small fraction of the data set. It will try to update its weight because it knows what the error is. It's going to compute gradients. It's going to do the backprop, and it'll compute the updated weights. So one option is that all the workers work in lockstep. So as everyone sees its group of 10 images, they update the weights, and then they do an all reduce. Everyone gets the latest and the latest estimate for what the entire network's weights are. So that's the synchronous model of execution. The other extreme is to do it asynchronously. So everyone has 10 images, say. They go ahead and they process their 10 images. As soon as they are done with the backprop, then they're going to just broadcast their updates to an asynchronous parameter server, and then it'll be the job of that parameter server to reconcile differences and send the updates out to the other nodes. So some trade-offs here. Again, these are two extremes. For synchronous scaling, where everyone is moving in lockstep, compared to a serial implementation, so if you were to do the same task on a single node, you will likely have the same number of iterations for convergence. The negatives, the downsides here are that if any one of your nodes fails for whatever reason or lags behind, that will essentially slow everyone down. Now, on the asynchronous side, you can move faster. Again, people are not constrained to block and communicate, so you can certainly move faster. There is more robustness to node failures. So if one of the nodes goes down, it's not the end of the world. But chances are high that you will need many, many more iterations to converge compared to the serial implementation. All right, so clearly we don't have to choose extremes. So you don't have to, I mean, this is a spectrum. You don't have to be fully synchronous or fully asynchronous. So you can be hybrid. And essentially, that's the strategy that we ended up going with. So we break up our supercomputer into groups, which are going to be executing synchronously. One of the nodes in that group will be responsible for communicating its updates, which reflect the latest updates for the compute group 1, to an asynchronous parameter server. And we'll see where that takes us. So we can change by changing the number of synchronous compute groups. We can essentially move along the spectrum. The other thing that we ended up doing, apart from this hybrid strategy, is to dedicate parameter servers for every layer of the network. So, for example, here in this schematic, there are 4 layers in the network. So we dedicate one parameter server to handle the traffic coming in from all of the different groups. Another node for the second layer, so on and so forth. There are some more advanced topology-aware placements. So exactly, you want to make sure that if you are within a synchronous group, then you don't really span racks on a supercomputer. So anyway, so we just make sure that when the runtime comes up, that we take the topology of the network into account and try to minimize extra hops. All right, so here are some results. So there are 2 configurations here. One is a strong scaling configuration wherein we fix the overall dataset size. And all we're going to be doing is to throw more and more nodes at the problem. So you would hope that things run faster and faster, at least the time to completion in terms of processing the dataset is faster. So sure enough, the synchronous approach stops scaling after some point. So as we go from, say, 256 to 512 nodes, the synchronous approach stops scaling after that and sort of flattens out till the 1024 node mark. But the hybrid strategy, wherein we played with having 2 groups, so 2 synchronous groups that would communicate with each other through through a parameter server, or 4 groups, that seems to scale better. Now, so this is most likely the configuration that you will likely have in your work. You'll have a certain dataset size, and you'll want to maybe throw more nodes at the problem. If you are at I guess, in a situation where you can come up with a weak scaling configuration, wherein each node will always have the same amount of data to process, but as I add more nodes, I can add more data. So that's the weak scaling configuration. Things seem to hold up fine for our implementation. So synchronous is in blue, and the hybrid strategy seems to be scaling better than the synchronous strategy. So anyway, so things seem to be holding up reasonably well. John, I guess, had a pointed question for me earlier on, well, I mean, does this converge at all? So you might be processing the same amount of data, but is your network converging? So for climate, we do see the loss dropping, and it seems to be leveling off. So the hybrid strategy seems to be to be holding up. Now, there is a slightly different problem where we applied exactly the same architecture. So the topology-aware placement, the hybrid tuning strategy, so on and so forth. I could not create the same plot for climate, but there is a different science problem in high-energy physics. And essentially, I think it does a nice job of visually representing what the difference might be between a synchronous run and a hybrid run with regards to convergence. So, the dotted blue lines are the worst case scenario for synchronous execution. So that's this case. So again, loss is plotted on the x-axis, and number of epochs or iterations is on the x-axis. Loss is on the y-axis. Solid blue lines is the best case for synchronous. So again, when you run on 9,000 nodes, not every run is going to be identical. So they're going to be stragglers, and they're going to be node failures, and so on and so forth. So the solid blue line is the best synchronous run. The dotted blue line is the worst synchronous run. And then we have hybrid in various flavors. So with 2 groups, with 4 groups, with 8 groups. And I guess if you look at the orange line, for example, and let's say that we care about this particular loss level, we want to get the loss to a certain level of acceptable performance. The orange line definitely gets to that loss level faster than the blue line. And there might be a gap of 1.66x in the number of iterations that it took for the synchronous to eventually catch up. Now, the async, which would be all 9,000 nodes doing their own thing, that will likely not converge, certainly in this time frame. So anyway, so there is a benefit to the hybrid model. All right, so just to recap overall performance. So on a single KNL node, we can get several teraflops. For the 9,600 node run, which ran on 600,000 plus cores, we were able to achieve 15 petaflop per second peak. And then on a sustained basis, we were able to get 13 petaflops or so. So just to conclude, I think I'm slowly getting out of time. So just to recap, I think there's a lot of, I think, genuine excitement in the field of AI and deep learning. A lot of breakthroughs in computer vision, in speech, and control systems. In this presentation, I think I wanted to communicate that we can get the same success in scientific data as well. So deep learning has now been established to be a viable tool for finding patterns in climate data set. And this can certainly help us enable to characterize better what climate change will do in the future. There were representational challenges in getting this to work. So I think we proved that supervised architectures can do a good job in terms of detecting known patterns. And then semi-supervised architectures can potentially discover new patterns in the future. In terms of computational challenges, I think we're certainly getting reasonable performance on a single KNL node. But then also, I believe this is the largest multi-node scaling experiment that's been done with deep learning so far. I want to thank a number of researchers from Intel, from Stanford, from Montreal, and of course, Berkeley Lab. All right, thanks very much. I'm happy to take questions.
Thanks, Prabhat. I had one question. So when do we start seeing the application of your models towards predicting actual, extreme weather events? And I'm sure you're also waiting for that so that you can actually test in your models in the real world.
Yeah, so I think the word prediction is unfortunately overloaded in the climate context. So in this case, we are not really doing prediction. We've already run the simulation out, and all we want to do is to find patterns in that simulation. So in some sense, the data set is fixed. That having been said, there are people who are trying to look at deep learning, so variants of convolutional and LSTM architectures for predicting the entire state of the system for the next few time steps. So that work is also in progress, and I think the results are promising. There are limits to the predictability of the climate system, and that's a property of the system itself. So it's a nonlinear, chaotic system. So we know that we cannot predict the state of the system beyond 2 weeks. But to what extent these convolutional LSTM architectures can do a good job, better than the climate models, that remains to be seen.
Curious if you saw in your kind of training in your encoder and autoencoder and de-encoder, any insights about the fundamental dimensionality of the data set, right? So you have this large...
I'm sorry, what was the question?
About any insights on the fundamental dimensionality of the data set, right? So like what's the minimum number of nodes that it can be brought down to?
Yeah, so in many ways, we did not want to artificially constrain the data set size, right? So the 768 by 768 image patch, that's the native spatial resolution of the data set. One could coarsen it, I guess, but we found that we were able to get autoencoders to work at that resolution reasonably well. And in terms of channels, again, we sort of stuck to the 16 channels that we had. It is, I know that if one wanted to train, say, 1K by 1K patches or higher, chances are that you'll have a hard time to get autoencoders to work.
We have time for one more question.
So I'm curious, the original input is actually an output of a simulation. So is just a visual representation? Why did you choose a visual representation, or are there other representations you could have used?
So the input is the simulation data. So the simulation produces grids, and the grids have 768 by 768 points. And then again, each point has 16 channels on it. So all I was doing in the movies is just creating a visual representation by mapping one field to an RGB image. But we actually do not create RGB images. We work on the raw double precision floating point data as is.
Cool. Let's thank Prabhat once again.
Cool.
And Prabhat would be hanging out here during the break for more questions. Thanks.